look at the next group of 5 from the Regents exam in June 2015. Question 11 is just a standard classic proportional parts, given a triangle with a triangle inside of it and the proportional parts, just find the pieces. There's a slight little twist to the question, but pretty standard. Number 12, we're in the business about right triangles and similarity. This particular question that's asking deals with the cofunctions between sine and cosine and their relationship in a triangle. Also pretty straightforward. In 13, we're in congruence, and we're in the C category because that's where we establish proof, but ultimately we're in that category because we're talking about quadrilaterals on one of those objectives. And so this one has to do with using the quadrilateral properties to establish what shape we're looking at. In 14, we are in equations, and it's classic. It's actually, I think it's the first objective in that particular area, A1, because that's where we learn about the equation of a circle and how to complete the square to obtain a radius and the center of the circle. Also fairly straightforward classic. SRTB is the business of giving some sides and angles and things and asking whether it's similar or not. Also, I think quite straightforward. The material handles every one of these questions with ease, with even greater complexity than what's being asked here. All right, let's look at question 11. It says, in the diagram of the triangle ABC, got some parallel lines and a few measurements. This is just a classic, what we call a side-splitting theorem problem. Proportional parts, where we have parallel lines cutting the sides into proportional pieces. There's different ways to approach this. You can just say 9:5 is 9.2 is to x, and get x, and then add it to 9.2 to get the entire length of AC. That's the one little trick there. They don't want the x here, they want the whole side AC. Another way to approach it is to embrace the full length AC. You could say 9 is to 14 as 9.2 is to AC, and straight up solve for AC. And we get this. Let's take a look at the materials to show you where the side-splitting theorem is and where we do a lot of questions like this. So you can see here that in this question we definitely establish the concepts of what's called the side-splitting theorem, where we look at the relationship of the pieces that are cut by that parallel line. So the side-splitting theorem is really at the heart of this particular question. We go through its proof comprehensively, and then of course we do plenty of questions that deal with all kinds of side-splitting items, somewhere the whole side's given and a piece is known, and vice versa, where you get a real good sense of this kind of question. This is a classic question, and so definitely we cover it in great detail. The student should succeed on this one quite easily. All right, in this question we're given a triangle. We're told it's a right triangle, and then it asks for what relationships we see. Of course, in a right triangle, the remaining acute angles are summed to 90, so we have an angle and then 90 minus that angle. And we learn in a right triangle of this type that sine and cosine are cofunctions of each other because they sum to 90. For instance, out of angle A, the sine of angle A is x over h, and from this corner, from B angle, the cosine of this angle is x over h. They're the same. So these two are cofunctions and must be the same. And in the notes and in the worksheets dealing with this objective, we definitely hit this kind of question and even more difficult ones than this. Part of this question, of course, is what we call cofunctions. The connection between two functions, how they interrelate. And the way we establish this in great depth is to look at a trig table of values and to have students notice that, hey, wait a minute, this number is found here, and it's found here, and it's found here, but it's also found over here, and so on. They get a quick idea that the sine of an angle is equal to the cosine of 90 minus that angle. And we establish in good detail, for sure, the ideas of why this is taking place. We talk about that we're in a triangle, and so looking at it from one angle is in relationship to looking at it from the other angle, and the relationship between cosine and sine. Worksheets do the same. We have kids find the matching values, and we talk about that relationship. We look at real easy relationships, then we look at the algebra ones too, that are often more difficult to students and a little more complex. But again, are focused nicely on that concept. Lots of good practice. All right, in question 13, we're dealing with a quadrilateral. It gives us some information about the diagonals, and then it says to basically prove or establish something's a parallelogram. So we would need to know the properties of a parallelogram to basically embrace it. It looks like it's giving us, let's see, which one is not sufficient. So bisecting and so on, two opposite equal pairs and so on. They give us a number of reasons for, and then number 4 is the one that is not. Embrace that. And you can see from the worksheets and the notes here that I'll show you that we definitely hit this idea strongly. This question definitely goes after the standard GCO C11. It talks about the quadrilaterals and their properties. We spend a lot of time establishing what those properties are. And then in this question, it's not just about establishing, knowing what properties are. It's kind of going in the reverse idea. So let me speed down here, where we start to say, okay, if we notice these things, then we can establish something's a parallelogram. So it's working backwards. There's also a number of other problems that deal the same way, where you're given some properties and asked to determine what kind of shape are we looking at. So this is more about working kind of backwards, the converse of the experience, to understand what would I need to know to establish something is a parallelogram. And there's plenty of materials found that do that. Question 14 embraces the equation of a circle and the use of completing the square to put it in a format where they can easily read the center and the radius. Of course, we get 16 as the value when it's all said and done here, and that's not the radius, but 4 squared is 16, so the radius is 4. That's why you see it being tested that 16 is the answer, but we learn that when it's all in its vertex or in its standard form, we learn that r squared is that value, and so that's why we say 4, not 16, the answer there. Let's look at a couple of examples where that's in the materials. So this particular question deals definitely with the equation of a circle, knowing its forms. So we establish how an equation of a circle comes about. We talk about the center and its radius. And then we get into completing the square, and that's what really is being asked in this question. Lots of examples, both the fractional ones and whole number ones, lots of things there in the worksheets. We give good examples of how to do a completing of the square and then attempt to work on it. This is basically the exact question that got asked. Beyond the worksheets, we have assessments, and those assessments and question banks have lots of questions based off of this idea of center and radius. Both given a point and a radius, what's the equation, and then working backwards from completing the square as well. Good support on this type of a question. Question 15 deals with the similarity of two triangles. They definitely kind of make them look so they're not necessarily similar or difficult to match them up. We are in the right cluster, no doubt about it. They give us some information. And then really we want to establish what we know for sure, and it says, given these lengths, which statement is true, and we are definitely able to establish that they're similar because the angles that match up and so on, and that they have the right proportions, and all those things work out nicely. Because you get the angle E and B are the same, and then we get AB being 9, BC being 15, DE being 6, and EF being 10. Now how you know who to match up is if you're the smallest one here, you have to be the smallest one in the other. So the 6 would go to the 9, the 10 would go to the 15, and we see 90 equaling 90, and the angle between them. So this is a side angle side situation,
and so that's why we know they're similar. And we'll look at how the notes definitely and worksheets handle this easily. The essence of this question is the side angle, side, side proportionality reasoning to determine similarity. In the notes we establish where those come from using the similarity transformations, and then we apply it, and mostly in the proof settings here, but certainly we establish why something is similar and what are the characteristics of similarity. So we don't just practice angle. We've got side angle side and a number of other ones that we use. Here's some just recognition, just like this question. Given some information about two triangles, can you establish that they are similar or not by what's your similarity statement, what's the criteria? Lots of good support there. In the assessment bank for this area, we have all kinds of multiple choice questions dealing with exactly this kind of question. So students are well prepared for this.